So we have proved this four function theorem, which states that if you have four functions defined on the subsets of bracket n, and if we satisfy this relation, then we can actually prove that it satisfies this relation over the arbitrary collection of subsets. Again, this collection is summation of all the values of alpha over the elements in this collection. So we have proved this four function theorem. But actually this theorem holds for more general structure than just the subsets of bracket n. So this is the set of all subsets of bracket n. But we can consider more general structure, which is called lattice. So lattice is a partially ordered set. Which we often just call poset. So partially ordered set is a collection of, it's a structure which are equipped with elements. Say X is a poset. It has a relation, this binary relation, over the elements of this set, which satisfies three conditions. First is that for any x is smaller than or equal to x in this relation, and if we have x and y, where x is smaller than or equal to y and y is smaller than or equal to x, then x and y are the same. Meaning that if two are different, then at least one of these two does not satisfy. And third is that the transitivity, if x is smaller than or equal to y and y is smaller than or equal to g, then x is smaller than or equal to g. If you have a structure, a collection of elements with a binary relation satisfying this, then we call this a poset. This is partially ordered set. For example, if we consider all subsets of bracket n, where we say this if and only if A is subset of B, then this forms a poset. It's easy to check all those three relation holds. So a lattice is a poset, and this is special poset which satisfies the following property as well. If you have elements, let's write it this way. Elements x and y, it has a unique minimal upper bound. X join y, called the join of x and y, and also it has a unique maximal lower bound, which we write this way, which we called the mid of x and y. So, what do you mean unique minimal upper bound? Is that we say x join y is G, meaning that its definition is that for all G prime satisfying x is smaller than or equal to G prime and y is smaller than or equal to G prime, then G prime is small, G is smaller than or equal to G. So this is minimality, and x is smaller than or equal to G, y is smaller than or equal to G. So this provides that this is an upper bound, and this says that this is minimal upper bound. So G is upper bound, and among all upper bounds of both of them, G is the smallest one. And this is unique. Then you say this is lattice. So for all x, y, such minimal upper bound uniquely exist. And similarly for join, you can flip this inequality to make sure that it is maximum lower bound. And let's say if you have a lattice, L is, we say, distributive. If the following holds, for all x, y, g in here, the element, if you consider this relation, then we if this holds, then we say that this is distributive. And this is also equivalent to that to have this inequality for all x, y, g. So this relation, this property and this property are equivalent. So if one holds, the other also holds. It's not too difficult to actually prove that. And if that property holds, then we say this is distributive. So it's like, so you can consider this. Oh, sorry. So I should have written this as a join. So you can consider these two as two different operations. And in high school or middle school, we learned that we have this distributive law for multiplication and addition. Similarly, we have two operations and one distributes into the other. And we can consider an example. Let's say, again, if you consider the collection of all subsets of bracket n with this set inclusion relation is a lattice. Moreover, it's a distributive lattice. If you have a two set x and y, its join is actually same with intersection in this case, and its mid is intersection and join is its union. It's easy to actually check that this is maximal upper bound and this is minimal lower bound. And also this distributive law holds with this relation. So for this, we define x join y b. For each element you take the join, and x mid y be that you take all the elements in this set and you take the join and you consider all such things. So let's define this way. Then if you go back to the four function theorem, this is about a special distributive lattice. So this is a distributive lattice, and this theorem is about special distributive lattice with this join and mid relation and join and mid relation. So what this means here, if you replace this with the join and mid with this new definition, then the above theorem works. And what we claim is that this four function theorem not only works for that 2 to the bracket n only, it works on any distributive lattice. So again, we have a finite distributive lattice L and four functions defined on L with say non-negative integer. Did we define? Give me a moment. Did we define on a non-negative real? Okay. So here we just write R plus, but let's use this to denote the non-negative real. So this obviously includes 0, because that's how we have used these functions in the proof. So this is non-negative real. Such that if we satisfy this condition, then for every collection of elements in this lattice, we have alpha x and beta y is at most gamma x join y delta x mid y. So we have this more general theorem. And the proof is not, how we get this theorem from the previous theorem is quite easy using the following fact. And we know that one of the theorem by Volkov, this is a standard result in process theory or lattice theory, is that we know that every finite distributive lattice L is actually isomorphic to a sublattice of 2 to the n for some n. So if you have any finite distributive lattice L, then it's just some sublattice of 2 to the n, 2 to the bracket n. So you consider, the corresponding 2 to the n, and you modify the definition of this so that this is defined on here. So it's actually defined on, let's just assume that the L lies inside of 2 to the n, and alpha, beta, gamma, delta are defined over L. Then you just redefine that on the entire this lattice, so that this has value 0 outside of F. Then you can still show that this holds. And then once you have this conclusion, that actually some inside of this L means exactly what we have here. So we can prove that this theorem actually holds. And you can look up this theorem, and then proof of this theorem is also not too difficult. So basically, if you have this L, which is distributive lattice, then there you can find some elements in L which cannot be written as a join of several other things. So they are like prime numbers in number theory, so which cannot be expressed as the join of other elements. And each of them, you consider them just like these elements in 2 to the n, and every other element can be expressed as a join of some of those. And you use that to actually, make a make a homomorphism between from L to 2 to the n by mapping these into some of the, elements here, and then you actually prove that that's what we desired. That's a basic, big picture, but you can look up the Volkov theorem and then check for yourself. Anyway, now we can come back to what we wanted to prove. So we wanted to prove the correlation inequality over graphs. So for, say, random graph, G and P, we want to prove that the probability that it is Hamiltonian, the event that this is Hamiltonian, and event that this is planar. And then we want to compare the probability that both of them happen with the probability that one of them happen, and you multiply. And we want to compare those two and then decide which one is bigger. For that, we wanted to actually prove the FKG inequality and use that to achieve what we want. So again, now we want to prove this FKG inequality. For that, we define one concept first. So last time we actually in here introduced this FKG, but there was some terminology that we didn't understand. But this finite distributive lattice we now understand, but we have to also know what log supermodular function is. So we say that a function say mu from L to non-negative in real, and let's say L is finite distributive lattice so that the join and mid are well defined. This is called log supermodular. If mu of x times mu of y is same as mu of x join y times mu of x mid y, and you compare them, then this part is bigger. This is called log supermodular because if you take a log on both sides, then you get log mu x plus log mu y and log mu x join y plus log mu x mid y. So if some function f satisfy this relation, then we say that this is supermodular. And then if this relation, the inequality is the other way, then submodular. And this terminology log supermodular comes from that it is supermodular once you take a log. And say a function f is increasing if whenever you take x and y where x is more than equal to y in the relationship with binary relation equipped with lattice, then we call this is an increasing function, and we call this decreasing if the other way around. So now, we consider the FKG inequality. And L is, again, finite distributive lattice. And mu is log supermodular. And for any two increasing function, what we have is the following. This term and we consider these two terms, then the right hand side is bigger than or equal to the left hand side. And proof is easy using the four function theorem. You consider alpha and beta to be the mu times g and mu times f and mu times g, and gamma is mu times f times g, and delta is mu. Then now we want to apply this theorem, four function theorem. For that we only have to check that this holds. Then we can conclude with this conclusion. So we want to check that this holds first. And for that we use the fact that mu is log supermodular, and then two functions are increasing. So for x and y in L, what do we have to compare? We have to compare f alpha x beta y with later say gamma x join y delta x mid y. So what's this? This is mu x f x mu y g y. And we have to use two things. One, log supermodularity. So you take these two and then you consider the log supermodularity. Then mu x join y fx gy mu x mid y. And we want to use the fact that the f and g are increasing. And we are proving this upper bound, so you take the something which is bigger. But now what's this? This is exactly gamma x join y, and this is exactly delta x mid y. So this holds. So thus the four function theorem implies that if you have a collection of all elements in L, then we have this inequality. But here, what's each term? This is alpha of L, this is beta of L, and this is gamma of L, this is delta of L, with this four definition. So this is exactly what we have here. So we prove the FKG inequality. So here, if both of them are decreasing, then we just follow the proof with switching the role of gamma and delta, then the inequality still holds. And if f is increasing and g is decreasing, then we can actually prove the inequality with a different direction. Because if g is decreasing, then we replace g with g prime, which is a k minus g, where k is large number, so that the k minus g takes a non-negative value. Then this is increasing function, and you can this is increasing function. So with this and this, you write down this inequality. And then because this part, you have a constant minus g. So you take care of the constant part and then move the g part on the other side, then you get this inequality. So if both of them are increasing or both of them are decreasing, then you will get this inequality. But one is increasing and one is decreasing, then you get the other side of the inequality. And now we, as I mentioned before, as we planned, we want to consider mu as a measure on L. So it's so you have this L, and we consider this as a probability space. So you will consider a probability measure on here. And using that, we have a probabilistic interpretation on here. So more generally, say, so again, when we want to, put some probabilistic interpretation on here, this f and g are not arbitrary one, but it's gonna be ones related to certain graph property at the end. So for that, we define the concept, the previous concept. So for example, here we have before we consider what's monotonically increasing and decreasing graph property. We want to consider this on a more general context. So let A be a family of, say, subsets of one set capital N. We say this is monotonically decreasing if we have set A lie in this, calligraphic A, and A prime is subset of A, implies that this A prime also lies in this calligraphic A. And similarly, we say it is monotonically increasing if the similar thing happens with the other side of the inequality. Now what we want to do is to consider the graph case. We consider the collection of all pairs. Then the above definition coincides with this definition for graph properties. And now from here, what we can prove is that, say, let's consider a real vector P1 to Pm, where each Pi is between 0 and 1. And now we consider a probability space. Whose elements are all members of subsets of this capital N, and for each A we consider the probability, let's say this vector is P, with respect to this P is for all I inside of A we multiply Pi. For all j not in A, we multiply all P1 minus Pj. And we define mu, which actually depends on the choice of this real vector P to non-negative real by this. Then we can actually check that this mu is log supermodular. We even can prove that not just inequality but equality also holds. And we apply the FKG inequality. Then what we have is that if we have A and B, we have two monotonically increasing families of subsets of this set capital N, and C and D be monotonically decreasing functions, families of subsets of N, then for any P, P1 to Pm, what we have is the following. The probability that if you randomly pick an element from here using this probability space, then the probability that the resulting one satisfy both calligraphic A and calligraphic B is bigger than or equal to the product of probability that is satisfied. It belongs to calligraphic A and calligraphic B, and you multiply those probability. And for both decreasing, this is also same. But if one is increasing and the other one is decreasing, then inequality is the other way around. So now, what? GNP, if you consider the random graph GNP, then this P, you can consider the vector which consists of the all elements here are just all coordinates here are same P. With that vector, and then N is 2 to the, N is same as bracket N choose 2. Then you have this model. And then you say that this A is about being Hamiltonian and C is being planar. And being Hamiltonian is monotonically increasing. If you have a Hamiltonian graph and you add some edges, then it is still Hamiltonian. And this is decreasing because if you have a planar graph and you delete some edges, this is still planar. Then you can see that the probability that it is Hamiltonian and planar is smaller than or equal to, you just compute the probability that it is Hamiltonian and compute the probability that it is planar, and then multiply it together. So if you take 1 and then you divide it, then you can actually prove that the probability that it is planar, assuming that this is Hamiltonian, is smaller than it is planar. So that's what we wanted to show. So depending on the whether the graph property is monotonically increasing or decreasing with these, we actually know which one out of these two are bigger. So that's something we wanted to prove in this section. And now we want to move on to section 7 about the martingale.